So as mentioned at the end of the last movie, we're now going to talk about how you can go from Lewis structures to predicting the three-dimensional shape of molecules. And we're going to use for that the so-called valence shell electron pair repulsion theory, first put together in the early 40s by H.M. Powell and Sidgwick, and then refined by a couple of great scientists, Nyholm and Gillespie, in the mid-1950s. With all that, those are four great scientists, but it always cracks me up that I think they called it the wrong thing, because instead of the valence shell electron pair repulsion, it really should be the valence shell electron group repulsion. So the acronym that you will be familiar with is VSEPR, VSEPR. That really should be VSEGR. But anyway, the idea is that electrons form groups around atoms that must be near each other. For example, a single bond is two electrons that are being shared between two atoms, so they have to be between those two atoms. Those electrons don't like each other, but they have to be close enough to each other to be seen by both nuclei. So therefore we say that the two electrons in a single bond constitute one group, because those two electrons have to be close to each other. A double bond, 4 electrons. However, they still have to be close to each other. They still have to be found between the two atoms that are double bonded together. And so they form one group. And that's why I like group instead of pair, because you start thinking about electron pair repulsion. Well, now a double bond is 2 pairs. No, a double bond is one group. A triple bond, 6 electrons even. All 6 of those electrons have to be between the two atoms that are bonded. So therefore they constitute one group. 3 pairs, one group. And then finally a lone pair, non-bonding electrons, as we said, pair up to make lone pairs. A lone pair is considered to be one group. And the shape of a molecule is determined by the electron group repulsion around a central atom. By central atom, I mean those with more than one bonded atom. A central atom versus a terminal atom. Okay, so rest of this movie is going to be talking about that, expanding it and doing examples. So we'll start off thinking about carbon dioxide. Carbon dioxide looks like this. You have a carbon that wants 4 bonds, 2 oxygens that each want 2 bonds. So the best way to draw it is to have a carbon double bonded to each of those oxygen atoms. Now, if I'd done this in class, and I assume I will have done this in class by the time we get to this, most of you would have drawn it like that. But there would be absolutely no problem if anyone had drawn it like this, because these are both fine Lewis structures. They both show the important things that you get from Lewis structures. A carbon atom bonded to 2 oxygens, a carbon atom bonded to 2 oxygens. Those bonds are double bonds. Those bonds are double bonds. Each oxygen has 2 lone pairs. Each oxygen has 2 lone pairs. Okay, so Lewis structure perspective, those are fine. However, from the VSEGR perspective, there is obviously a significant difference between them, because these look different. They have different shapes. So applying VSEGR, first thing we do is we look at what is the non-terminal atom, because the shape of the molecule is going to be based upon how those groups of electrons arrange themselves around a non-terminal, a central atom. So the central atom is C. Okay, C has got 2 groups of electrons around it, one group there, one group there. Okay, so 2 groups of electrons, and those 2 groups of electrons around that carbon want to get as far apart as possible. Well, the best way for them to get as far apart as possible is, of course, this 180-degree straight line. Okay, if we look here, lone pair there, or sorry, group of electrons there, group of electrons there, group of electrons there and there. These are much closer to each other than these are. Best way for 2 groups of electrons to get as far apart as possible is in this structure here. We're going to start compiling a VSEGR chart for the different options in how many groups of electrons there are around a central atom and how those groups arrange themselves. So we're always going to be interested in how many groups of electrons do we have. In this case, we have 2. Okay, and those 2 groups of electrons arrange themselves in what we would call a linear fashion. Should be fairly obvious to you. Okay, here is a linear object, a line. Central atom there, 2 groups of electrons, one there, one there. Okay, and we're also going to define our geometry in terms of the angle, and the angle is always going to be the angle at that central atom, which in this case is 180 degrees, the angle between the groups of electrons. BH3 is a molecule that we will not have drawn in our Lewis structure discussion because it's actually a little bit complicated to draw if you apply what we think of with Lewis structures. But I bet if I'd asked you to draw it, you would have drawn this. Boron in the middle of the 3 hydrogens. Boron has 3 valence electrons, so it uses 1 each to make the bonds to the hydrogen. Hydrogen, of course, just wants 1 bond each. Now, if we apply VSEGR to this, the non-terminal atom, the central atom, is B. How many groups of electrons are there? 1, 2, 3 groups of electrons around the boron. How do 3 groups of electrons arrange themselves? What's the best way for them to get as far apart as possible? And the answer is to form this sort of little triangular shape here, Mercedes-Benz symbol. Boron in the middle of the 3 hydrogens. It is a planar shape, as I tried to show in this little photograph here. Okay, all 4 of the atoms are in a plane and the angles between them are 120 degrees. So moving to our little chart, you have 3 groups of electrons. That geometry is called trigonal for 3, planar because they're in a plane, and it looks like this, and the angles there between each of these groups of electrons, 120 degrees. Now, another one that I would not have asked you to draw because it can get rather complicated, and we'll talk about how we would draw it when we get into the next year of study, SO2. But when you draw it like this. You have a sulfur in the middle that still has a lone pair of electrons. It's got a single bond to an oxygen and a double bond to another oxygen. Central atom, according to VSEGR, is the sulfur. Now, how many groups of electrons are there around the sulfur? Pause and then answer. So back from the pause, I hope. How many groups of electrons around the sulfur? 1 for the single bond, 1 for the double bond, and 1 for the lone pair. So there are still 3 groups of electrons around our central atom here. And those 3 groups of electrons are going to arrange themselves in a trigonal planar. However, let's look at what this is then. You've got the sulfur going to 1 oxygen, that's 1 group. Sulfur going to another oxygen, that's the other group. Sulfur going to the lone pair, that's the 3rd group. Okay, but you don't see the lone pair. The lone pair is on the sulfur. You just see the effect of that lone pair repelling the other groups of electrons. So the actual shape of SO2 is like this. There's the sulfur, there's the 2 groups that go to the atoms, and then the bonding, the lone pair, the non-bonding group, is up here. You don't see it, you just see its effect repelling things. Even though there's 2 atoms bonded to the sulfur, it's not linear because there is this 3rd group here doing the repulsions. So now we need to modify our chart a little bit, because we got to not just be concerned with how many electron groups there are, we have to worry about whether those electron groups are bonding groups or lone pairs. Okay, the ones we've already done, we haven't had lone pairs. CO2, the 2 groups went to bonds. It was the carbon bonding to the oxygen. And so the shape of that particular molecule is indeed linear. When we go for the BF3, okay, the boron here, 3 hydrogens, all 3 of the bonding groups were bonding groups. It was the boron bonding to hydrogen for all 3 groups, and so the shape of that molecule was trigonal planar, no problem with that. But now we got a situation where we got 3 groups of electrons, so those electron groups arrange themselves in a trigonal planar fashion. But only 2 of those groups are bonding groups going to the oxygens in the SO2. One of them's a lone pair. And so what that looks like is still the trigonal planar, but instead of a bond here, a lone pair. You don't see the lone pair, you just see the effect. And so this is now got the same electronic geometry because there's still 3 groups of electrons, but the shape of the molecule is different because you don't see one of the groups of electrons. We describe this shape as bent or angular. Now, what would you say the angle here is between? Now, it's important that we say we're talking about the angle between the bonding groups because we don't see this one up here. So what's the angle between these bonding groups? What's the angle oxygen, sulfur, oxygen? And you'd say, well, it's 120, right? Because it comes from trigonal planar. Well, it's actually a bit less than 120. It's about 118 because lone pairs, because they're right on the atom, are more repulsive than bonding groups. In bonding groups, the electrons that are repelling each other are between the atoms. In a lone pair, it's right on the atom. So the lone pair is more electron density, it is more repulsive, and so it bends these bonding groups a little bit further away from itself, a little bit closer to each other to give us 118 degrees. Two groups of electrons, really dead easy. Both of them will be bonding groups, otherwise there's no point to it. When you got three, you can have three bonding groups and no lone pairs, two bonding groups, one lone pair. In each case, the electron groups are trigonal planar, but in one of the cases you don't see one of the electron groups because it's a lone pair, so its shape is different, its shape is bent. So we've done two groups of electrons, we've done three groups of electrons. You don't have to be a superstar genius to imagine we're now going to talk about four groups of electrons. Best initial illustration of this is CH4. Lewis structure, that is that. From the VSEGR perspective, the carbon is in the middle and it has 1, 2, 3, 4 groups of electrons around it. What's the best group to arrange four groups of electrons around a central atom? Is it going to be this two-dimensional structure where each angle is 90 degrees? And the answer is no. You can actually get these further apart than 90 degrees when you go into 3 dimensions in what is called a tetrahedron. Now, tetrahedron, you got a central atom, in this case the carbon, and one way to picture it is you got one atom going straight up. I know it's not quite straight up, excuse the effects of gravity when we've taken this picture. Anyway, so one going straight up and then the other three arranged in a little triangular arrangement, not a flat triangular arrangement, but a bent down triangular arrangement. So a lot of times people think of this as being a triangular based pyramid. Okay. Various ways to think of it. This is the best way to draw it. So you've got one going vertically in plane, another one coming down also in the plane. Illustrated, the angle between them is greater than 90 degrees. Then there's one that comes out at you. This one here, the way we draw coming out at you is with a black wedge like this. And then one going away from you, which we're drawing as this dotted line wedge. If we were in class, I would illustrate a tetrahedron by embarrassing myself and adopting what I call a cheerleader pose, okay, which kind of looks like this. What I do is I take my legs and spread them apart so that my front foot is coming at you, my rear foot is going away from you, and then perpendicular to my feet, I just have my hands, my arms spread out as if I'm doing a sort of little cheer type thing, which is why we call it. Okay, so arms spread out, making a V, legs, one in front, one behind. So that's a tetrahedron. We got model kits that we gave you that you can use to make tetrahedra, and we will of course illustrate it more in class. Filling out our VSEGR chart then. Now we're up to 4 groups of electrons. The way you arrange 4 groups of electrons is tetrahedrally. Now, when all 4 of those groups of electrons are bonding groups, well then the molecule looks like a tetrahedron as well, because we can see atoms at the end of each of those bonding groups, so it's tetrahedral. And the angle in a tetrahedron, 109.5. Remember, we need it to be bigger than 90. 90 is what you get if you go in 2 dimensions. Wrapping up with our examples, we will look at 2 more molecules that have 4 groups of electrons but have an increasing number of lone pairs. Start off with NH3, there's the picture. Nitrogen is obviously the non-terminal atom. 1, 2, 3, 4 groups of electrons around that nitrogen, so therefore it is of course tetrahedral. But we do not see one of those groups because it's a lone pair. We only see 3 of the groups. And so this is what it looks like. It is a tetrahedron where we've lost the top. That's where my assistant was very conveniently holding it. Okay, so you've got 1, 2, 3 bonding groups, but they're not in a plane. They're sort of bent away from that lone pair. Okay, so that's 3 and 1. 3 bonding groups, 1 lone pair. This is called a trigonal pyramid. And then we go for everybody's favorite covalent molecule, water. Draw it out. Oxygen is the central atom, the non-terminal atom. 1, 2, 3, 4 groups of electrons still around the oxygen. But now there are 2 lone pairs and 2 bonds. And so when we remove off 2 of those bonding groups, putting behind the lone pairs, we're left with 2 groups here that I haven't put a little photo of it because it is the same concept. It is a bent or an angular structure. So filling out the VSEGR chart, we've still got 4 groups of electrons, but now the first example, NH3, 3 are bonding, 1 is a lone pair, looks like that, trigonal pyramidal. What are the angles going to be in there? Well, because the lone pair is more repulsive, it's going to push these closer to each other, so the angles will be a little bit less than 109.5, they're about 107 typically. And then the other example, water, 2 groups of electrons, 2 lone pairs, bent angular structure, and the angle in this is definitely going to be less than 109.5 because now we've got 2 lone pairs pushing these things away from the lone pairs, thus pushing the bonding groups together. So the actual angle is about 104.5 in water. So we need to build some model kits. That's why we gave them to you for part of this reason. And we will do some more practice from Lewis structures going to shapes in class. Hope you had fun.